Hello and welcome to Weapons of Math Instruction. This is the 7th and final video in our week-long celebration of Pi Day. If you missed my other 6 videos in this series, you can find them on my Facebook page or my YouTube channel. This video specifically references the last one, which was on the Wallis formula for pi. In this video, we're going to look at a derivation of the Wallis formula that came not from pure mathematics, but rather from quantum mechanics. The derivation appeared in a 2015 article in the Journal of Mathematical Physics. Before I get to the derivation, I need to go over some background information on a special function in mathematics called the gamma function. It requires an understanding of improper integrals, such as will be covered in Calculus 2. So here it is. The gamma function, gamma of z, equals the integral from 0 to infinity of x to the z minus 1 e to the negative x dx. So this is an improper integral because its upper limit is infinity. I want to show you 2 special cases and 2 properties of this function. We'll need them when we look at the derivation of the Wallis formula in the second segment. Special case 1, gamma of 1 equals 1. Plugging in z equals 1 gives me this integral, which I'll treat as an improper integral in the usual way. And here I've evaluated the antiderivative, which is negative e to the negative x. And then I evaluate the limit, which is 1. This exponential goes to 0 as t goes to infinity, leaving us with just the 1. Special case 2, gamma of 1/2 equals the square root of pi. This one's harder. Here's what I get when I plug 1/2 into the gamma function. This is not an elementary integral, but it becomes more approachable with a change of variable. I'm going to let x equal u squared and dx equal 2u du. And here's what I get when I make the substitution. If I put u squared in for x right here, I get u to the negative 1. If I put u squared in for x here, I get e to the negative u squared. And dx equals 2u du, which goes right here. Now this u to the negative 1 will cancel with this u right here, and this 2 can go in front of the integral. So here's what I get when I do that. Now this integrand is an even function of u, which means that its integral from 0 to infinity is equal to its integral from negative infinity to 0. That means that I can get rid of this factor of 2 by integrating from negative infinity to positive infinity of the same integrand. This is the well-known Gaussian integral. Evaluating it requires techniques from Calculus 3, and I can spend a whole video explaining how to do it. Just so we don't go too far down the rabbit hole, I will at this point tell you the answer and ask you to remind me that I owe you a video on this integral in the future. This integral evaluates to the square root of pi. So those are the 2 special cases. Now let's look at the 2 properties of the gamma function. Property 1, gamma of z plus 1 equals z times gamma of z. So here's gamma of z plus 1. And here's how we treat the improper integral. And we're going to integrate this by parts. And here are the parts. Now we'll apply the integration by parts formula as we erase the parts off the board. Otherwise this is going to get real cluttered real quick. And here's what I get when I do that. Now this limit here is 0. Why? Well, on one end, as t goes to infinity, the monomial term can't keep up with the decaying exponential, and so the whole thing gets dragged to 0. And on the other end, if we plug in 0 for x here, we get 0 automatically. And this, by definition, is just z times gamma of z. So there we have property 1. Property 2 is really just the special case of property 1 where z is a natural number. If that's the case, then gamma of z plus 1 equals z factorial. Let's see why that is. So first of all, we'll invoke property 1. Then we invoke property 1 again. If I apply property 1 to gamma of z, I get z minus 1 times gamma of z minus 1. Continuing this process means we just keep piling out factors outside the gamma function, and we keep reducing the argument of the gamma function until we get down to 1. Now we know what gamma of 1 is from the previous slide. It's 1. So I'll make that substitution. And what we're looking at right here is nothing other than z factorial. Now we'll look at the quantum mechanical derivation of the Wallis formula for pi. The 2015 paper that we'll be looking at was written by Tamar Friedman and C.R. Hagen. Here's the reference in case you want to look it up. In this paper, they examined the ground state energy of the hydrogen atom. Specifically, by calculating a limit comparison of the minimization of the expectation value of the energy with the known exact value of the ground state energy, they derived the Wallis formula for pi. Let's take a look at the paper. So I've got the paper right here. The hardest part of making this video was deciding where to start presenting the derivation from. Starting it from the beginning of the paper wouldn't be possible in a short video. There are just too many details to unpack. So I'll walk you through the early parts of the paper, and we'll go back to the slides when we reach the point where we'll start looking at the guts of the derivation. So here, they present the Schrödinger equation for the hydrogen atom. H is a mathematical operator called the Hamiltonian, and this Greek letter psi is the atomic wave function. The explicit form of H is given here in parentheses. The first term is the kinetic energy term, and the second term is the potential energy term. When H acts on psi, it returns the total energy E times psi. Now, because the electron moves around the nucleus, spherical coordinates are the best coordinate system to use. Those coordinates are the radial coordinate r, which is right here, and two angular coordinates, which you can think of as latitude and longitude, like on the Earth. We won't need those coordinates for our discussion here. This equation is for the radial part of the Hamiltonian. What they're doing here is computing the expectation value of the Hamiltonian, which, as I just mentioned, gives the total energy of the atomic electron. And here, they minimize that expectation value. And as you can see, this expression contains gamma functions. The minimal energy state of a hydrogen atom is also called the ground state. Now, the energy levels of a hydrogen atom are known exactly, and they're given by this formula right here. In the subscript, n sub r is the radial quantum number, and L is the orbital quantum number. The ground state occurs when the radial quantum number is 0, and so this is the formula for the ground state energy. Here, they take the ratio of the minimized expectation value for the energy and the ground state energy, which is the minimum value of the energy, and they form that ratio right here. And then they take the limit as L approaches infinity, and that limit has to be 1. And this is where we're going to start looking closely at the derivation. So from the paper, here's the minimized expectation value of the energy, and here's the exact value of the minimal energy state, aka the ground state. In these formulas, m is the electron mass, E is the electron charge, and h bar equals h over 2 pi, and h is Planck's constant. These are fundamental physical constants, and these are what make the equations of physics different from mathematical equations. Physical equations have empirical content, whereas the equations of pure mathematics are based on a priori definitions without referencing the natural world. L is the orbital quantum number, as I mentioned, and the only thing that you need to know about it is that it is a natural number. Okay, let's get to it. Here is the limit from the paper. We'll start by substituting the expressions for the minimized expectation value of the energy and the ground state energy. It's just a matter of dividing two fractions. Here's what I get when I do that. Notice that all of the fundamental physical constants have canceled out. This goes a long way towards explaining how we can get a purely mathematical result from a physical system. Next, we need to simplify the gamma functions in the brackets here and here. The first one is easy. Since L is a natural number, the second property of gamma functions that I showed you in the first segment says that gamma of L plus 1 is L factorial, which is this right here. This one here will take more work. L plus 3 halves is not a natural number, so I can't use property 2 of the gamma function. I can, however, use property 1 by noting that L plus 3 halves is just L plus 1 half plus 1. And letting Z equals L plus 1 half, I apply property 1 to get this. Continued application of the first property of gamma functions results in these factors being piled up and the argument of the gamma function being reduced by 1 until it reaches 1 half. at which point we can stop because we know what gamma of 1/2 is from the first segment. It's the square root of pi right here. And to make life simpler, I'm going to combine the terms of the first two factors with a common denominator so that every factor has a denominator of 2. With these simplifications, our limit now looks like this. Now this becomes an exercise in juggling factors. What I'll do in the next step is I'll bring the L plus 1 squared right here inside the brackets as L plus 1. And I will square this square root of pi and bring it outside the limit as pi. And here's what I get. The next thing that I'll do is I'll take all these factors of 2 in the denominators of the denominator, and I'll bring them up to the numerator. I'll do that by doubling each factor in the numerator like so. And here's what I get. Now, because this bracket is squared, there are 2 of each of these factors in the numerator, and there are also 2 of each of these factors in the denominator. And I'm going to play a little game of musical chairs by grouping these factors together. One of the 2's in the numerator will sit over this 1, and the other 2 will sit over one of the 3's in the denominator. I'll play the same game with the 4's and the 6's in the numerator, and so on. Eventually, I will get to 2L over 2L minus 1 times 2L over 2L plus 1. And we'll find that when the music stops, 3 factors are left without a chair. These 2 factors of 2L plus 2 from the numerator, and this 1 factor of 2L plus 1 from the denominator. And those will sit right here. This product in brackets should be recognizable as a truncated version of the Wallis product from the last video, so I'll go ahead and use the big pi notation formula. Now it's time to take the limit as L goes to infinity. When we take the limit of the finite product, we get the infinite product. And when we take the limit of this expression, we get 2. And that 2 is sitting right here. So we have 2 over pi times the Wallis product equals 1. In the final step, multiply both sides by pi over 2, and this completes the derivation. This concludes my 7-video series on Pi Day. I really hope you enjoyed watching these videos as much as I enjoyed making them. Thanks again, and I'll talk to you soon. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.